Hi everyone, Dr. Burns here with our first lesson in Chapter 7, where we're going to be learning about molecular geometry, intermolecular forces, and bonding theories. In this lesson, we're going to be focusing only on molecular geometry. This chapter has a lot to do with our structures, our Lewis structures that we've learned about in our previous chapters, and is mainly focused on kind of the shapes of those. So some students find this a little complicated because we're looking at shapes and not so much at numbers anymore. So if you need to pause the video at any point, rewind it, feel free. Okay, we have to learn these shapes and these structures to help us with what we're doing next. So we have to master this first, and for some students that can be a little bit complex, but don't worry, we'll get through it together. Okay, so we've talked about Lewis structures, and our Lewis structures are going to predict the structures of our molecules, but we've only looked at those in 2 dimensions. Now we know that in our natural world, we don't live in 2 dimensions, we live in 3, right? We have multiple dimensions to us. So we have to think about these Lewis structures in a slightly different way. So that brings in our molecular structure, where we think about the VSEPR theory, V-S-E-P-R, valence shell electron pair repulsion. And this theory predicts our structures of molecules in 3 dimensions. So let's look at the name, valence shell. So that's talking about our electrons in our valence shell. So outer electrons. Electron pairs, we know that we're talking about pairs of electrons, so that's going to be bonds and lone pairs. Okay, those are all where our electrons are being paired up. And then we're talking about repulsions, right? Because like repels like, so like charges repel. So the electrons are going to be repelling each other. Okay, so they're going to organize themselves in these 3-dimensional structures so that they are oriented in a way that they are repelling the most. They are furthest away from the other electrons in the structures. So I have the example here of methane, or CH4. And if we follow our Lewis structure drawing rules, this would be our structure. CH4, there's 8 electrons that have to be shared. So we have 4 bonds, so each of those bonds has 2 electrons, 1, 2, 3, 4, 5, 6, 7, 8 electrons total. Okay, so that is a valid Lewis structure. However, when we think about 3 dimensions, we have to think a little bit differently. So if we look at the Lewis structure of methane here, if we were to look at the angles between these bonds, so between this bond and this bond, okay, that would be an angle that looks like 90 degrees. Because when we were drawing Lewis structures, we said to think of this like a box. You draw each bond coming out of each side of each box, and therefore that leads us with bond angles of 90 degrees. But here is the VSEPR model of CH4. Okay, so here's carbon, and these are all the hydrogens. And I have it in a 3-dimensional structure, because we can now move our hydrogens backwards and forwards so that the electrons in our bonds can all repel each other as much as possible. So these angles between these bonds are now greater than 90 degrees because we have more room to work with when we're talking about 3 dimensions. Okay, so while Lewis structures can show us our basic structure as we're writing it down on a piece of paper where I can't really show 3 dimensions, our VSEPR theory is going to predict that shape of that molecule now in 3 dimensions. We can draw our Lewis structures to try to show these 3 dimensions. So if I tried to show this in methane in 3 dimensions, I would put like the hydrogen at the top, and then I would kind of put the rest of the hydrogens down to show that they are repelling that upper hydrogen. And if we're thinking 3 dimensions, these are also repelling each other. It's not perfect, and if you're not an artist, don't worry about it. You can continuously draw your Lewis structures with those 90-degree bond angles as long as you remember that these are actually 3-dimensional structures and they have different bond angles than what you draw in your Lewis structures. Okay. So the basis of the VSEPR model is that the electrons repel each other, right? The R stands for repel. So where do we find electrons in our molecules? Well, we said that the electron pair, that was lone pairs, and bonds. So anywhere that we have a pair of electrons, we have a specific name for it called a domain or a group. Okay, so an electron domain, so if I spell that right, or an electron group. Different textbooks, different places online call them different things, usually an electron domain or electron group. Okay, so they are the same thing when we talk about that. So our different types of electron domains would be a lone pair, or we could have our bonds, our single, our double, or our triple bonds. So let's look at these structures and let's predict, or let's count how many different electron domains they have. So in CO2, this is carbon dioxide, my electrons are in a double bond and a double bond. Now, a double bond counts as one electron domain. As does a triple bond. Because it's an area, domain means an area at which there are electrons. It doesn't matter how many electrons there are. Okay, so a double bond is still considered one electron domain, as is a single bond. So CO2 has 2 electron domains. It has 2 regions in that molecule that have electrons in bonds. And we're talking specifically in this about these electron domains on the central atom, on the atom that's in the center. Okay, that's how we're determining our shapes and our geometries is based off of the central atom. So it doesn't matter that this oxygen has a double bond and then lone pairs, because we're not determining the geometry of the oxygen, we're determining the geometry of the central atom, carbon. Another way that I like to think about this is think of an electron domain as an electron direction. How many different directions are the electrons going off of the central atom? Well, the electrons are going this way and that way off of the central atom. There's still electrons there. It doesn't matter how many there are, whether that's in a single, a double, or a triple bond. They're still going in 2 opposite directions. So there's 2 electron directions. The electrons are going in 2 opposite directions. So there are 2 electron domains. Our next structure is ozone, O3, and we want to determine how many electron domains it has. Well, we're talking about this central oxygen here. Okay, so how many different domains of electrons does this oxygen have? Well, in our previous example, we said that a double bond is an electron domain that counts as 1, as does a single bond. So a single bond is also just 1 electron domain. But also on this oxygen, we have a lone pair, and a lone pair is also considered an electron domain. So on this central oxygen, we have 3 electron domains. Okay, the difference between a bond and a lone pair doesn't matter because the electrons are localized in 3 different directions or 3 different areas. We have the electrons going in this direction, and that direction. Doesn't matter if they're going towards a bond or towards a lone pair. And again, it doesn't matter that these oxygens have lone pairs on them because we're not looking at the geometry of the outside oxygens, okay, the peripheral oxygens. We're only looking at the geometry of the central oxygen. So the central oxygen has 3 electron domains, 1 double bond, 1 single bond, and 1 lone pair. Our final example here is NH3. So we're looking at the number of domains off of the nitrogen. Okay, so we have 3 bonds coming off of the nitrogen, as well as a lone pair. So NH3 has 4 electron domains. Okay, because it has electrons going in 1, 2, 3, 4 directions. So we have 3 single bonds and 1 lone pair on our central nitrogen. Okay, determining the number of lone pair, or electron domains, I should say, is very important for determining the geometries of our molecular structures. So let's jump into what those molecular structures and what those geometries are. So for now, as we're learning this, we're going to be focusing on determining the structures of molecules with a very general formula of ABX. A is our central atom, B are the atoms around it, and X is going to be an integer between 2 and 6. So here are 5 different options for our AB notation. We have AB2, AB3, AB4, AB5, and AB6. So this basically says that there is a central atom A, and there's 2 B atoms that surround it. Okay, for right now, we're going to assume that we have enough electrons to make those bonds. There's going to be no lone pairs on what we're talking about for right now. We're just going to look at the basic structure of ABX. We're not going to worry about double, triple bonds. We're not going to worry about lone pairs or anything like that. Okay, so let's start off with AB2. So when there are 2 electron groups around the central atom, they will occupy positions on opposite sides of the central atom. This results in the electron groups taking on a linear shape with a bond angle of 180 degrees. So because there are only 2 bonds, okay, in our examples here, those electrons in those bonds are going to repel as much as possible. And the largest angle we can have between them is 180 degrees. So that's the maximum angle that we're going to see between different bonds. As we go down, we're going to see that bond angle decrease and decrease. Okay, so we have 180 degrees between those 2 bonds, meaning that they're forming a linear structure. Okay, they essentially draw a line. Now, I have 2 examples here. I have BeCl2 and CO2. So we can see, if I erase these, then it doesn't matter if there's a single bond or a double bond, okay, because we're still just talking about 2 electron groups or 2 electron domains. The number of bonds within that domain doesn't matter, right? Because the electrons in BeCl2 are going this direction, and in CO2 are also going in that direction. It doesn't matter that one is in a single bond and another is in a double bond, okay? So both of these structures would have a linear geometry. So we can say shape, or we could say geometry with a bond angle of 180 degrees. So we refer to this as a linear molecule. That is the name of the structure, linear. It is a linear molecular shape. Next up, we have AB3. So this is now 3 electron groups or 3 electron domains around the central atom. Okay, so when there are 3 electron groups around the central atom, they will occupy positions in the shape of a triangle around the central atom. Okay, so here we see our triangle. This results in the electron groups taking on a trigonal planar shape or geometry with a bond angle of 120 degrees. Okay, so we have 3 groups now. They're going to form an equilateral triangle, And those angles are all going to be 120 degrees. So see, we're decreasing from 180 from our linear, now we're at 120. So we're going to see that bond angle continue to decrease as we add more and more groups off of that central atom. So the name of this, again, chemists are not very creative in their naming. Okay, so we get trigonal because it makes a triangle. And we get planar because all of the electron groups are in the same plane. So that's what this little balloon drawing here is. Okay, it shows all of the electron groups and how they are in the same plane as each other. Okay, the furthest way that they can repel is 120 degrees, all within the same plane of each other. That's the furthest they can get. If I tried to move one of them up here, okay, then these two would adjust. If you actually think about putting balloons together, that's actually what happens. Okay, so this is called a trigonal planar geometry, and that's for 3 electron groups. Okay, remember tri is 3, trigonal means triangle. Okay, so it's 3 electron groups around our central atom. Okay, next up we have AB4, and this is where there are 4 electron groups around the central atom, they will occupy positions in the shape of a tetrahedron around the central atom. This results in the electron groups taking on a tetrahedral geometry with a bond angle of 109.5 degrees Celsius. Okay, so this is going to be our first structure where our electron groups are coming out of plane. So our last two, everything was in the same plane, and now we're out of plane because after 120 degrees, if I added another electron group, in order for them to repel as much as possible, they need to be in different planes. Hence why the three-dimensional theory of VSEPR is very useful because we need to show that repulsion. Okay, so we see that again in our balloon diagram here. I added that 4th group, and now all of those balloons are repelling each other, and they're at a bond angle of 109.5. So we're still decreasing our bond angle, okay, from 180, now we're at 109.5. That 0.5 is not always important. Usually 109 is acceptable. And this is called a tetrahedral shape. Tetrahedral shape. This was the shape of CH4 that we drew before. So this would be my very bad drawing of CH4. Okay, so this is a tetrahedral shape. This is when I have 4 electron groups around the central atom. Now those electron groups don't have to all be the same. So we could have 4 electron groups, there we go. We could have CH2 Cl2, it doesn't matter, okay, even though these chlorines have lone pairs on them, okay, it doesn't matter what those peripheral groups are, it doesn't matter what they are, it doesn't matter if they're the same or not, there's still 4 different directions that the electrons are going in this structure. Who cares what the electrons are going towards? Okay, we'll take a look at that in a future lesson, okay, but for what we're doing for molecular structure purposes, if the electrons are going in 4 different directions, or in any direction, this applies to all of our structures in our geometries, all of those atoms don't need to be the same. It doesn't change the structure in any way, okay? So, our next group is going to be our AB5. Okay, so when there are 5 electron groups around the central atom, they will occupy positions in the shape of 2 pyramids that are base to base with the central atom in the center of the shared base. There shouldn't be a D there. This results in the electron groups taking a trigonal bipyramidal geometry with bond angles of 90 degrees Celsius and 100 degrees Celsius. So, before we jump into what all of that means, I want to note that this is for any of our expanded octets. So we talked about expanded octets in our previous lessons in a different chapter. Okay, but our expanded octets are the ones that are going to have either our AB5 or our AB6 notation, right? Because that would mean that there's 5 electron domains around that central atom, right? So we have AB5. Automatically, no matter what those B's are, we already know that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons around that central atom, and they're all going in different directions. Okay, so we have 5 different electron domains, meaning we already know we have an expanded octet. Okay, so for this, the structure is 2 pyramids that are base to base. Now, I'm not good at drawing, but I will try. Okay, so there's one pyramid, and then we draw another one down here. So we have an element here, an element there, an element there, an element here, an element down there. And then there's one in the back, which I can't draw, so I'll draw that as a small dot. Okay, this one right here where they meet in the middle, that's going to be our central atom. Okay, so that's this guy here. And then everything around it is our peripheral atoms. So they have 2 different degrees for bond angles. They have 90 degrees, which are going to be between these top one and any of these side atoms. Okay, these are all 90 degrees. And then the angles between all of the atoms that are kind of in the center here is 120 degrees. So we say this is trigonal because we're making triangles, right? And it's bipyramidal because they're in a pyramid shape. Maybe I can draw this better on this structure here where they have some dimension. Okay, so we have a pyramid here. Okay, that's one pyramid. And then we have a pyramid here, which I can't draw as well. Okay, balls there. So we have 2 pyramids that are stuck together, base to base. So we have bipyramidal, 2 pyramids. So tri meaning 3 for triangle, bi meaning 2. Okay, so that can remind us of our 5 electron domains. 3 plus 2 is 5. Okay, so here we have the example of PCl5 where we can see those groups aligning well. We have those 3 groups that are 120 degrees from each other and those 2 groups that are 90 degrees from each other. Okay, before we move on to the AB6, I want to just make another comment about those specific bond angles in AB5. So the AB5 molecules are going to contain 2 different bond angles between their adjacent bonds. We have specific names for those positions that the atoms are in, okay, and that helps us determine what those bond angles are. So we have first our equatorial positions, which is going to be our 3 bonds, so I'll label those with E's. Okay, if you think of this kind of like a sphere, or if there was a sphere around this, like the Earth, we have the things that go around the center are going to be like the equator, so they're equatorial. Those are going to be the elements or the atoms that are in the center of the structure that go around kind of the entire outside. So, and those are going to be the 3 bonds that are arranged in a trigonal plane. So they're all in the same plane. They make up a triangle. That's that base of that pyramid. Okay? They're all at 120 degrees from each other. So these are the 120 degrees ones. Our other 2 atoms are known as are in the axial positions. Okay, so here are axial. Think of this again like a globe. They're on the axis of that Earth where they're spinning from. So this is where they're going to be spinning around if we were to spin this entire molecule around. Okay, this is like the axis. When I move these, they kind of stay in the same spot, and the only atoms that we see moving are going to be the equatorial ones that are going to be spinning around that axis. So these are the axial positions. These are the ones that are going to create the 90-degree angles with the equatorial atoms. So this is again our trigonal bipyramidal shape. our last molecular structure is going to be the AB6. And this is, again, our expanded octet. Okay, so when there are 6 electron groups around the central atom, they will occupy positions in the shape of 2 square-based pyramids that are base to base with the central atom in the center. This results in the electron groups taking on an octahedral geometry with a bond angle of 90 degrees Celsius. Okay, so we have, again, we're having those pyramids, but now they're in a square arrangement. Okay, again, I'm not great at drawing, but we can see that nice square pyramid there. Okay, there's just 2 of those. There's one on the top and there's one on the bottom here. Okay, so we have 2 square-based pyramids. This doesn't have a name that relates to pyramids. It more so pertains to the number of sides. It's octahedral because each of these have 4 sides. So there's 1, 2, 3, 4 sides on the top and 4 sides on the bottom. So that would be 8 sides. Another way that some textbooks use to describe this is that there's 2 tetrahedrons that are put together. So 2 times 4 is 8 for octahedral. So our octahedral geometry has bond angles of only 90 degrees between their adjacent bonds. An example of this is SF6. So we see that there, again, we have 2 atoms that are in what we're seeing as axial, but we don't call them axial because this is fully symmetric. So if I rotated this, if I were to rotate the entire molecule, I could see these as the axial, and then everything else would be in a square plane. Okay, so we don't define these as axial versus equatorial for our structure here because they all have the same bond angle as well. Okay. So we've talked about all of these. We had AB2, which is linear, AB3, 3, which is trigonal planar. We had AB4, which is tetrahedral. And we have AB5, which is trigonal bipyramidal. And our last one was AB6, which is octahedral. So, again, these all were based off of the number of electron domains that surrounded the central atom. So to practice this, let's draw our Lewis structures for each of the structures below, and then use that structure to determine the electron domain geometry. Now, it's very important that we draw the correct Lewis structure, which includes drawing our lone pairs in the correct positions, because if we're missing a bond or we're missing a lone pair, that's going to affect our number of electron domains, which is going to affect how we're going to identify the electron domain geometry. Okay, so we need to first follow our rules for drawing Lewis structures. So let's start. CH3I. So we have 4 electrons from the carbon, 3 electrons from the 3 hydrogens, and 7 electrons from the iodine, which gives us 14 electrons. So we're going to start with drawing carbon in the center. We have 3 hydrogens and an iodine. That used up 8 electrons. So I have 6 left. I have to complete my octet on my iodine. 1, 2, 3, 4, 5, 6. That used up all of my electrons. Okay. So now that I have my full structure, I can look at my central atom of carbon and say, how many electron domains does it have? Well, it has a single bond, a single bond, a single bond, and a single bond. So it has 4 electron domains. So of these, of our AB notations, the one with AB4 is going to be our correct answer. So this would be tetrahedral. Okay. Next up we have H2S. So we have 2 electrons from the hydrogen, 6 electrons from the sulfur, leaving us with 8 electrons total. So we have S, H, and H. I can only bond those H's once, so I used up 4 electrons. I have 4 left over, so I'm going to use those 4 to complete my octet on my sulfur. So if we look at our electron domains, 2 of them are going to be from bonds, and 2 of them are going to be from lone pairs. Remember, lone pairs can still be electron domains. So in total, we have 4 electron domains. Okay, 2 of those are from bonds, 2 are from lone pairs. But it doesn't matter if they're a bond or a lone pair, as we talked about with counting our electron domains earlier. So our notation that has 4 electron domains is again AB4, or tetrahedral. So this answer would be tetrahedral. Okay, so we can have the same electron domain geometry even though we have completely different looking structures, because electron domains can be identified as either bonds or lone pairs. Okay, let's look at an ion. Ions are still going to have a molecular shape that's going to follow our same notation. So we have NH4. So we have nitrogen, which has 5. We have the 4 hydrogens, which contribute 4 electrons, but we have a plus charge here, so we have to remember to subtract 1 electron. If it has a positive charge, that means we removed electrons. It's a +1, so we removed 1 electron. So in total, we have 8 electrons to work with here. So our structure is N with 4 hydrogens. We're going to cover with a plus. I used up all of my 8 in drawing those bonds. I drew 4 bonds. There are 8 electrons in those bonds. So to look at our geometry, well, that nitrogen has 4 electron domains again. Meaning it is tetrahedral. Okay, so it doesn't matter if it's an ion. The fact that it's an ion doesn't affect its structure. In terms of its geometry structure, it'll affect the Lewis structure, obviously. We talked about that previously, because it'll change our number of electrons. But in terms of the geometry, the fact that it's an ion doesn't affect it either. Okay, so we have 4 different examples of molecules that all have tetrahedral geometry, 4 electron domains, that all look a little bit different. Okay, so let's keep practicing. Given the following Lewis structures, determine the number of electron domains and the electron domain geometry. Okay, so here we have carbon is our central atom. How many electron domains does it have? Well, it has a single bond, a single bond, a single bond, and a single bond. So that's 4 electron domains. As we know from our previous examples, that would be tetrahedral. Okay, so for these last 3 structures, what I want you to do is pause your video and determine the number of electron domains and the electron domain geometry for each of them. Our second example here has a triple bond. And as we said before, it doesn't matter if it's a single, a double, or a triple bond. This just counts as 1 electron domain because the electrons are all localized in the same region or going in the same direction, all towards that nitrogen. So this carbon has an electron domain through the triple bond as well as through the single bond. So it has 2 domains. And if it has 2 domains, it's AB2 which is linear, which we can see from that structure. It makes a nice line. Okay, our next example, we have the central nitrogen, which has a double bond, a single bond, and a single bond, okay, coming off of it. So that's 3 domains. That's AB2 for our structure. Okay, or sorry, AB3, I should say. Goodness. AB3 for our structure. So AB3, that's going to be trigonal planar. Okay, in our last example, we have carbon with a single bond, a double bond, and a single bond. So that's again 3 domains. 3 domains corresponds to trigonal planar. Now don't worry, we will have a lot more practice with our different types of electron domains and all the different types, AB2 through AB6, throughout this lecture. But what I want to talk about before we do that is the difference in the types of geometries depending on the structure. So what we've been looking at currently is the electron domain geometry, where we take every electron domain into account that is around that central atom. So this is going to be our lone pairs and our bonds. Okay, when there's a lone pair on the central atom, that's going to change things a little bit. So another geometry that we look at is the molecular geometry. And this is strictly looking at the arrangement of the bonded atoms. So this is where we omit lone pairs. And as we'll see, even though we're omitting them from determining the geometry, they still play a role in how the angles are calculated. So in an ABX molecule, the bond angle is the angle between 2 adjacent AB bonds. Okay, so we talked about that. Linear has 180. Trigonal planar has 120. Tetrahedral has 109.5. Trigonal bipyramidal is the one where we have axial and equatorial atoms, so they have 2 different angles of 90 and 120. And octahedral has 90 degrees amongst all of our adjacent atoms. Okay, so when the central atom in an ABX molecule has 1 or more lone pair, the electron domain geometry and the molecular geometry are not going to be the same, because the molecular geometry only cares about bonded atoms. Okay, so here we have ozone again, O3. And we said that this has 3 electron domains. We said that earlier in our lecture. So if it's 3 electron domains, the electron domain geometry would be trigonal planar. Okay, because we have an electron domain here, here, and there. When we go to molecular geometry, though, we only care about the atoms that are bonded. So we only care about this bond and that bond, which, looking at the difference, we see is not the same shape as a trigonal planar. Now, what I said before, where the lone pairs still play a role, that's because they're still here. Okay, I'm going to draw them here. And they're still affecting the bond angles, right? There's still an angle between them. It's not like when we go to do molecular geometry, the lone pairs disappear and I'm left with that. Okay, it doesn't turn to linear. Okay, so the lone pairs still play a role, but all we're looking at is where the bonds are going. So we're looking at where the bonds are in relation to that central atom. Okay, so the lone pairs don't just disappear, they still play a role. We're only looking at where the bonds are in that specific atom, molecule. So when we're looking at the example of ozone here, let me erase some of these lines since it gets a little confusing here. Okay, we have our 2 bonds. This creates a structure that we call bent, okay, because it looks like a bent molecule. It looks like I took it and I bent it, okay? So when we have an electron domain geometry of AB3 and it has one lone pair on the central atom, the molecular geometry then becomes bent. Now this applies to each of our geometries. So what we're going to do next is go through each geometry and talk about how adding lone pairs affects the structure and the molecular geometry and the specific names we have for the molecular geometries. Okay, so we first looked at our trigonal pyramidal. Our linear molecules will never have lone pairs, so don't worry about linear. It's always going to be linear. Okay, there will be no lone pairs there. Next up, we have tetrahedral. So this is going to be our AB4. Okay, so our electron domain geometry for all of these is still going to be tetrahedral, but now we're going to add lone pairs. So when I add one lone pair, this is going to be one lone pair, 3 bonds. We can see that we're still forming that tetrahedral shape. You can see that by the little green triangle here. Okay, we're still forming that tetrahedral shape when one of those bonds is replaced with a lone pair. But if I look at just the bonds, okay, they're still creating a triangle, but they're out of plane. Okay, they are no longer in plane like trigonal planar would be, okay, because those lone pairs are still playing a role, they're still affecting the repulsion of the electrons in those bonds, okay, so our molecular geometry shape is now trigonal pyramidal. Trigonal still meaning 3, there's 3 bonds that are playing a role. Pyramidal, for this, means that they are out of plane, making a pyramid. Okay, so they kind of make a little pyramid there. It's smaller in comparison to the other ones that we looked at, but it's still a pyramid because they're coming out of plane. So that's one lone pair. We can also replace another one of these bonds with another lone pair, so that brings us to our next example where we have 2 lone pairs and 2 bonds. Okay, this is the structure of water. So water's electron domain geometry is tetrahedral. Okay, it still has 4 electron domains around it. 2 of those just happen to be lone pairs. So if we look at just our bonds, okay, we see that we have 1 bond and 1 bond. Okay, so our 2 bonds are now making up another bent structure. So we have 2 versions of a bent structure. We differentiate them because this bond angle is 109.5. So they're still keeping a similar bond angle to their original electron domain geometry. Okay, so that's how we can tell the difference between our bents. Our bent up here, this has an angle of 120 degrees. Okay, so when we have 2 lone pairs and 2 bonds, that's going to be a bent geometry. It still looks like a bent molecule. Okay, let's move on to our AB5. This one we're going to have even more because with each new bonding group or each new electron domain, we can replace it with more lone pairs. So we have AB5, and again, this is going to be our expanded octets. We can still have expanded octets even if some of those electron domains are lone pairs. Okay, we can still have expanded octets for AB5. Okay, so our electron domain geometry for these with 5 electron domains is still trigonal bipyramidal. Remember, tri for 3, bi for 2 equals 5. Okay, so let's add 1 lone pair and 4 bonds. So instead of having 5 bonds, we're going to replace one of those with a lone pair and have 4 bonds left. Now, we said that AB5 molecules have 2 different types of atoms. We have our axial and our equatorial. When we are adding a lone pair onto our AB5s, okay, the lone pairs are going to go on the equator first. And this is so that we can have our best amount of repulsion. Okay, so if we put them up on an axial, which is the example we have here, okay, there are now 3 90-degree angles that are repelling those lone pairs. Okay, lone pairs are strictly electrons. They're not wrapped up in a bond being shared or anything like that. So they want to repel them more. We don't prefer lone pairs. Okay, so by adding it to the equatorial, there's only two 90-degree repulsions in that molecule, so that's limiting our number of repulsions, which is preferred. So we want to limit our repulsions with lone pairs. Okay, so that lone pair goes on the equator first, okay, on the equatorial atoms first. So when we have one lone pair and 4 bonds, our molecular geometry becomes a seesaw. And if you were to spin this, I can try to draw it the best I can. So here's our central. There's 1, there's 2. And then has 2 going off this way. That's just if I rotated this. Okay, we see that one linear portion here is now turned here. Okay, this literally looks like if I put a person here and a person here, it looks like a little seesaw. So again, we're not that creative with our naming, us chemists. So that is a seesaw shape. Okay, so that's one lone pair. What if we bumped it up to 2 lone pairs? So that's our next example down here. So we still have a trigonal bipyramidal. These are all trigonal bipyramidal. We just have 2 lone pairs and 3 bonds. So again, that's still equaling 5. Okay, again, our lone pairs are going to go on the equator. Okay, that's just minimizing our repulsions. Okay, so the molecular geometry, if I were to just look at the bonds, this is now called a T shape because it literally looks like a T. All of those atoms are in plane with each other. Okay, we're now in the same plane, so they make a T shape. Again, not creative with our names. And finally, our last example has 3 lone pairs and 2 bonds. So our last lone pair gets added to the equator. Okay, and my bonded atoms now are just in a straight line, which is linear. So just like we started with. So as we add more and more lone pairs, we're simplifying that structure more and more, and we usually end up in either a bent or a linear structure. Okay, so that was all of our AB5s. Okay, so we went from 1 lone pair, 2 lone pairs, to 3 lone pairs. Okay, we went seesaw, T-shaped to linear. Now we're going to look at our AB6. So AB6. So our lone pair gets added on. It doesn't matter where because all of the bond angles are the same. Okay, so we went from octahedral when we added that lone pair. So now we have 1 lone pair and 5 bonds. So still 6 electron domains for an octahedral electron domain geometry. For our molecular geometry, this now becomes square pyramidal because we make a square which then form a pyramid. Okay, so we just removed that other half of that pyramid by removing that lone pair. So if we're looking at just where the bonded atoms are, it makes a square pyramidal shape. So that's 1 lone pair. Next up, we have 2 lone pairs and 4 bonds. Okay, so it's still octahedral for its electron domain geometry because it still has 6 electron domains. But now our molecular geometry, if we look at just the bonds, we have a square planar structure. Okay, this is because the lone pairs are actually being added 180 degrees from the other ones. So this is where, this is the only step where adding that lone pair matters. Okay, so they're going to add to the opposite side of each other to minimize those repulsions again. So because we added them down here first, the next one are going to go up here. Okay, they can't go here or anything like that. So by putting the lone pairs 180 degrees from each other, we're minimizing the repulsions both with the bonds as well as with the other lone pair. Okay, so this creates, again, we keep that square, but now we get rid of the pyramid portion. So we got rid of this portion here. So we're left with a square. All of our atoms are arranged in a square, and they're all in plane. So we get square, planar. Square because there's 4 of them, planar because they're all in the same plane. Okay. Our last 2 examples are similar to what we saw. Oops, let me get rid of this. We don't need that yet. Ignore this. We don't need this portion yet. Okay. Sorry, that's a typo from a previous class. Our last 2 examples are what we saw before with the AB5 notation. So if I added another lone pair onto here, so if I created this to be a lone pair instead of a fluorine, okay, that would get rid of this guy, and our shape would then be in a T, so we get another T shape. So this is 3 lone pairs and 3 bonds. Okay, that's T-shaped. So I have 3 bonds, they're going to form a T shape. And then if I were to get rid of another one, so if I were to add another lone pair, I would add it directly across. Okay, that would get rid of that fluorine, and I'm left with a linear structure. Okay, so this would be 4 lone pairs and 2 bonds. Okay, so you see that we keep simplifying, and then the shapes start to be the same. So our atoms that obey the octet, they're going to end up in a bent structure, and our atoms that are expanded octets, they end up in a linear structure. So now I've provided a table. This table, I believe, is in your note pack as well as in our test taking materials. It's given to you on your ALEKS exams. You're given this chart here. We haven't learned about this column yet. Don't cross it out on your own. You're going to need it for this chapter, but for right now I'm crossing it out because you won't need it right now, so it doesn't make sense to you. Okay, you will need it, so don't cross it out on your own, or I'll uncross it out. Okay, so we don't get confused, but we don't know what that column means yet. We will learn about that in this chapter. But this tells us a guide of all of our different geometries. Now, this column here, this is just our electron domain geometries. So if I'm looking for just electron domains, I only care about this column because it directly relates the electron domain number to that. Okay, so if I'm asking for electron domains, I don't care if they're bonds, if they're lone pairs, whatever, I am asking strictly about that first column. If I'm talking about molecular geometries and we start adding lone pairs, well, then we're talking about everything here. Okay, so this is when we start adding lone pairs. Okay, and I'm asking about the molecular geometry. We can have times where the electron domain geometry and the molecular geometry are the same. That would be when we don't have any lone pairs. So the only time they are the same is when there are no lone pairs. Okay, which is the step right here. So when we're determining our geometries, the first step that we want to do is draw our Lewis structures. We have to make sure we have an accurate Lewis structure because we have to account for lone pairs on our central atom properly. If we're missing those lone pairs or have too many, then we're not going to have the correct structure or the correct name. We then want to count the number of electron domains, both lone pairs and bonds, in order to determine the electron domain geometry. Okay, so that's again just talking about this one. That's our step 1. If there are no lone pairs on the central atom, then the electron domain geometry is going to equal our molecular geometry. They will be the same. But if there are one or more lone pairs on the central atom, then you have to use the chart to find the molecular geometry. So that's all here for step 4. So if you have lone pairs, you're going to want to look in that portion of the chart when I ask specifically for the molecular geometry. So if we're asking for electron domain geometries, it doesn't matter if there's bonds versus lone pairs, it's not going to change the geometry. But if I'm asking about the molecular geometry, the lone pairs matter. Okay, so let's practice that. So we have PCl3 is an industrial chemical used in many herbicides and insecticides. The electron domain geometry of PCl3 is what? And the molecular geometry is what? So let's look back. Our first step is to draw the Lewis structure and then count the number of electron domains, and that's going to give us our electron domain geometry. So let's do that. PCl3, draw our Lewis structure. So phosphorus gives us 5 electrons, and then we get 3 times 7 from the chlorine, so we have 26 electrons in total. So we do phosphorus with 3 chlorines around it, so that uses up 6 electrons. I have 20 left. I need to complete my octets on my chlorines. That uses up 18. I have 2 electrons left. I'm going to put those right on my phosphorus in order to complete my octet. Okay, so that is my structure here. Now again, this is a perfect example of why we need to follow our Lewis structure rules for drawing this, because some students look at this and say, oh, it's PCl3. Done. Which is incorrect because you're not accounting for your lone pairs. Your lone pairs are going to be important. Okay, so our electron domain geometry for this one, well, if I have a bond, I have 3 bonds and 1 lone pair, that means I have 4 domains. Okay, so 4 domains for the electron domain geometry is then tetrahedral. For the molecular geometry, we have 3 bonds, 1 lone pair. Well, let's go to our chart. So, I have 4 electron domains, so I know I'm in this column here, or this row. Okay, so my electron domain geometry was tetrahedral. We just determined that. I now have to look at how many lone pairs I have. Well, we said we had 3 bonds and 1 lone pair, so 1 lone pair is here. That corresponds to this box here. Probably shouldn't use blue because it's a blue box. Okay, so our molecular geometry is trigonal pyramidal. Okay, so we see that. If we compare our structures, we have 1, 2, 3 bonds and 1 lone pair. Okay, so this is trigonal pyramidal. So our best answer for this would be C, tetrahedral and trigonal pyramidal. Okay, let's keep practicing. So, for the following Lewis structures, determine the electron domain and the molecular geometries. Okay, so for our first molecule here, we have 1, 2, 3, 4 electron domains. Okay, all of our angles look correct. We have 109 degrees between all of those. So our electron domain geometry is going to be tetrahedral. Okay, and our molecular geometry is also going to be tetrahedral. Okay, Now, what I want you to do for these next three is use your chart from your Notepack or your test-taking resources and determine both the electron domain and the molecular geometries. I will point out on our third structure here, the only way I'm able to get these bond angles the way they are is if we have a lone pair there, which they don't show. Okay, the rest of these are all at typical angles, so we have 120 and 90, so there aren't any lone pairs on those. We know that because of the angles. Okay, for this one we knew that we had to have a lone pair. For this third one we knew we needed to have a lone pair because I have 90, 90, 90, and 90, and 90, which is not a valid structure, so we have to put our lone pair there. So keep that in mind as you go to answer this question, that there is a lone pair on the bottom of that structure. Okay, our next example has 1, 2, 3 electron domains. So our electron domain geometry is trigonal planar. Okay, we know this because we have 3 electron domains and they're all in the same plane and they make a triangle. Okay, so they're all in the same plane. Okay. Since there are no lone pairs, the molecular geometry is also trigonal planar. Okay, our next one, the one with the secret lone pairs. Our electron domain geometry, well, we have 1, 2, 3, 4, 5, 6 electron domains. Those lone pairs count as an electron domain. So this is octahedral. 6 electron domains is octahedral. If we have 5 bonds and 1 lone pair, that means our molecular geometry is square pyramidal. Let's look at that. I'm going to erase my lone pairs for this because they don't matter for our molecular. I make a square out of my base, and then they all connect to the top to make a pyramid. So square, pyramidal. Our last one, the electron domain geometry, well, I have 1, 2, 3, 4, 5, 6 electron domains again, so this would be octahedral. And the molecular geometry is the same because there are no lone pairs. It would also be octahedral. Okay, let's keep going. For the given molecules, draw the Lewis structure and determine the molecular geometry of each structure. Okay, so what I want you to do, pause the video, draw out your Lewis structures for these first, then try to find your molecular geometries. This first structure, we need to draw our Lewis structure properly. We have to count our electrons. There's 34 electrons total in this structure. So we have the selenium in the middle. We have the 4 fluorines around it. Okay, and those all have lone pairs on them. I think for time purposes, I'm not going to draw my outside halogens with lone pairs anymore, just for this portion when we're practicing, okay? But when we do that, we use up 32 electrons, so I have 2 electrons left over. So they are going to go on the selenium as a lone pair. So that means I have 5 electron domains, 4 are bonds, 1 is a lone pair, which corresponds to a seesaw geometry. Okay, so that's 4 bonds, 1 lone pair. That's a seesaw. Okay, this is why following our Lewis structure rules is very important, because our structure or our formula doesn't tell us anything about lone pairs. So if we just go off of our formula and say there's 4 fluorines coming off of that, therefore it's tetrahedral, then is not correct. Okay, so let's look at the next one. SiCl4, there's 32 electrons here. We have an Si with Cl's. Imagine that those Cl's all have lone pairs around them, but for time purposes, I'm not going to draw them. There's no lone pairs on my silicon, so I have 4 bonds, no lone pairs, making this tetrahedral. Okay, we did PCl3 before. Do you remember what that one was? Did you look back in your notes to show that it was PCl3? Imagine some lone pairs on there, but then there was the lone pair on the phosphorus. Did you remember that? Okay, so that one is going to be 3 bonds, 1 lone pair, leading to a trigonal pyramidal. Okay, we did that one earlier. Okay, and then we have XeF4. So this one, lone pairs matter. We have Xe. I'm going to try to draw this as dimensional as I can. Okay, then we have 2 lone pairs on the xenon. Did you get the 2 lone pairs on that xenon from your count? Okay, so that's 2 lone pairs, 4 bonds, which gives us square planar. Okay, square planar because these fluorines all form a square and they are in the same plane. Okay, so that's octahedral for our electron domain geometry, but since I have 2 lone pairs, that becomes square planar. Okay. Now, let's talk a little bit about bond angles and the effect that lone pairs and multiple bonds have on those angles. So we said that they don't matter for terms of electron domains, which is true, but they do change our bond angles a little bit more because they have a little bit more electrons. So if you think about it, lone pairs are going to take up more space than bonded pairs of electrons, right? Because they're in kind of their own little bubble. They're not being shared or anything. So they are just by themselves. So they take up more space. And multiple bonds repel more strongly than single bonds because they have more electrons. Right? So if you look at this structure here, I have 2 electrons in that bond, 2 electrons in that bond or that domain. But in our double bond of C double bonded to an O, I have 1, 2, 3, 4 electrons. So if I'm looking at electron domains, I have 4 electrons in this domain, but only 2 here and 2 here. So they're going to repel much more than if that was just a single bond. Okay, so we see that the bond angles become affected by that fact. So let's start at the beginning. We have NH3. So this would be tetrahedral for an electron domain, which gives us an angle of 109.5. But because I put a lone pair on there, they're going to force, this lone pair is going to force these bonds closer to the other bonds, creating a bond angle of 107 degrees C, or degrees Celsius. We are not doing temperatures, my goodness. So 107 degrees. Okay, it's not a big change, it's not a huge change, but it changes it. Okay, so you have to remember that. For this one, we have SF4. Okay, we have a lone pair, again, on our central atom there. So what that's going to do is start to repel these bonds, those F bonds, but then because those are being repelled, it's then going to repel these as well. Okay, so we went from having 180 degrees now to now having 170 degrees, and from having 120 degrees to having 101 degrees. Okay, so they do change it. Now, I'm not looking for you to memorize the specific numbers. So, okay, so I don't need you to remember that 180 turns into 173.1. You do not need to remember that. What I want you to understand is that because lone pairs take up more space, they cause a larger repulsion, therefore changing those bond angles, making them smaller. Okay? So the same thing goes for our BF5 here. With our double bond example here at the end, okay, with CH2O, what normally would be 120 degrees, so this is normally 120, is now 122 because the 4 electrons in these bonds are pushing these down more. Okay, so it's then decreasing this bond, which was 120. This is now 116. Okay, so the bonds between the hydrogens, okay, it becomes smaller because the bond between the oxygen and the hydrogen becomes larger. They're repelling it more. Okay, so we just have to remember that because of those repulsions, those angles are changing. Okay, and I believe your chart does have those changes in angles. They say that it's going to be less than those specific numbers, which will help you see that, visualize that from that chart, because you have that chart on your tests. Okay, so make sure you utilize that. Okay, so we've been talking about all of these molecules with a central atom, but we know that in our natural world, not every molecule has one atom in the center with 4 atoms coming off of it. Okay, it's never that simple. So we need to talk about our molecular shapes when we have molecules with multiple central atoms. So when I have 2 or more central atoms, how do we determine the shape of those central atoms? So, the geometry of more complex molecules can be determined by treating them as though they have multiple central atoms. So here I have an example where I have 2 central atoms, one being a carbon and one being an oxygen. What we're going to do is just treat those as if they're their own central atom. So if we look at the carbon, I have my electron domains going in 1, 2, 3, 4 directions. It doesn't matter that when I go this direction, that oxygen has something coming off of it, because that hydrogen is not touching that carbon. They don't touch each other, therefore it doesn't count toward its electron domains. Okay? It doesn't matter that that oxygen has 2 lone pairs coming off of it, because those lone pairs are on the oxygen, not on the carbon. So, we still look at the number of electron domains. This is where thinking about them as directions is useful. So if my electrons are going in 4 different directions, it just doesn't matter what comes after the next atom. It doesn't matter that that oxygen is bound to a hydrogen. It doesn't matter that that oxygen has lone pairs on it. It does not matter, okay? So if I treat this carbon as its own central atom, it has 4 electron domains, meaning its electron domain geometry is a tetrahedral, and the molecular geometry is also tetrahedral, because there is no lone pairs on the central atom. Now, if we look at the oxygen and treat it as its own central atom, well, I have electrons going in 1, 2, 3, 4 directions. Again, it doesn't matter that when I go this way, this carbon is attached to 4 hydrogens. Those hydrogens are not touching that oxygen in any way. So they're not considered as being a part of that oxygen's geometry. Okay? So it doesn't matter that that carbon has anything coming off of it. We just want to look at the way the electrons are going. And in this case, it's 4 different directions, 2 of which are in bonds, 2 of which are in lone pairs. So my electron domain geometry is for 4 electron domains, which is tetrahedral. My molecular geometry is now 2 bonds, 2 lone pairs. So that would be a bent geometry. Okay, so that oxygen has a bent geometry. That carbon has a tetrahedral geometry. It does not matter that they are attached to each other. Okay, so let's keep practicing that. Let's determine the electron domain geometry of the labeled carbon in aspartic acid. So let's look at this carbon here. Determine the electron domain geometry of that carbon. Now the first thing you're going to want to do is check your octets. When you're given a structure, check your octets. We know carbon won't have an expanded octet, so we're looking for it to have 8 electrons around it. Well, it has 1, 2, 3, 4 bonds. Each bond has 2 electrons, so it has 8 bonds total, or 8 electrons total. So we have an octet around that carbon. Because what we'll find on some of these structures is they don't show their lone pairs. So let's look at this oxygen here, for example. The oxygen has 1, 2 bonds, which would only be 4 electrons. Obviously, we're not going to have a structure that doesn't obey the octet rule, so we'd have to infer that there are 2 sets of lone pairs on that oxygen. Okay, so even though we're not drawing the Lewis structure here, if it's given to us, we just want to double check our octets. So let's get back to the question at hand though. What is the electron domain geometry around this carbon? So it doesn't need any lone pairs. We said that it has 2 single bonds and a double bond. So determine the electron domain geometry of that carbon. If it has 3 electron domains, then it would be trigonoplanar. Okay, and if we were talking about the molecular geometry, it would also be trigonoplanar because there are no lone pairs. Okay, let's keep on going. Okay, for this molecule, we want to describe the geometry of each central atom. Now I'll label these for you. This is oxygen, this is carbon, this is carbon, this is nitrogen, and these white guys are hydrogens. Okay, so the first thing we want to do is check our octets. Since we're going to be describing the geometry of each central atom, okay, the oxygen, the 2 carbons, and the nitrogen, okay, we want to just double check that we have all of our octets complete so we know our lone pairs. So pause your video and put your lone pairs on these atoms so that they complete their octets. Some may not need octet or lone pairs, some may. They may need 1, they may need 2. Okay, so just double check that everything has an octet. Our oxygen only has 2 bonds, so it needs 2 sets of lone pairs to complete its octet, and the nitrogen only has 3 bonds, so it needs 1 lone pair to complete its octet. The carbons all have octets, they all have 4 bonds to them. This molecule does follow our rules. It follows our rules of atoms where nitrogen wants to have 3 bonds and a lone pair, and oxygen wants to have 2 bonds and 2 lone pairs, and carbon has no lone pairs and 4 bonds. So it does follow those rules, so you can always use those to back you up on these. Okay, so now that we know where our lone pairs are, we can now determine the geometry. Now I didn't specify the geometry, so let's do both. Let's do electron domain and the molecular geometry, okay, just to get the practice in. So let's go left to right. Let's do the oxygen first. Our oxygen, for the electron domain, it has 1, 2, 3, 4 domains. So if it has 4 domains, that would be tetrahedral. For the molecular, well, it has lone pairs, so we know that the geometries are not going to be the same. If I have 2 bonds and 2 lone pairs on a tetrahedral structure, this is going to be bent, which we can see because if I try to connect these bonds, they make a bent structure. Okay, it's a bent line. Okay, next up, let's do carbon. Carbon, for its electron domain, well, it has 1, 2, 3, 4. Yes, there's one hiding in the back there. So it has 4 electron domains, so it is tetrahedral. And since there's no lone pairs, the molecular geometry is also tetrahedral. The same goes for this carbon. It has 4 bonds, no lone pairs, so the electron domain and the molecular geometry are both tetrahedral. Okay, they're the same for each carbon. And finally, for the nitrogen, so for electron domains, it has 1, 2, 3, 4. 4 electron domains. Again, tetrahedral. But since there's a lone pair on there, our molecular geometry is going to be different. So 3 bonds, 1 lone pair is trigonal, pyramidal. Okay. So keep using that chart. If you know how to use it, you'll find it very useful for your exams. Okay. Now I want to start putting this all together. So we're going to take what we learned in our past few chapters and we're going to put it all together. So first, what we're going to do in this example is draw the Lewis structure for each of the molecules below and then name them. Name each of them using our rules for naming covalent compounds. These are all covalent compounds because Lewis structures show bonds. Bonds are between nonmetals. Okay, so that's a covalent compound. Okay, so these are covalent compound naming rules. So we want to draw the Lewis structures and then the compound name. So pause your video now and do that. Okay, for time purposes, I'm just going to draw the Lewis structures so that you can check your own work for Lewis structures. If your Lewis structure doesn't match mine, please make sure you're checking your Lewis structure rules to make sure you followed them accordingly. So SiCl4 looks like this. We're going to pretend that there's lone pairs on those chlorines that I'm just not going to draw today for time purposes. Okay, we have AsF3. There's a lone pair on that arsenic there. Finally, we have PCl5. And you'll notice I try to draw these in a way that gives me a hint towards their structure. Again, if you're not that great of an artist, it doesn't have to work out that way as long as you're able to determine your number of electron domains, whether they're bonds or lone pairs, and you know where they are. That's all that matters. Okay, so let's name these. So we have silicon, tetrachloride. So remember, if it's the first one and there's only one of them, we don't use mono. So it's silicon, we name it as is. Our next one we're going to name but add IDE to the end, so that would be chloride. And then to the front we add the number. There's 4 of them, so that would be tetra. Remember, we use the Greek prefixes, so tetra, not quad. So tetrachloride. Here we have arsenic trifluoride. Tri meaning 3, adding the IDE to the fluorine ending. So instead of fluorine, it's fluoride. Arsenic trifluoride. And finally, we have phosphorus. Pentachloride. Okay. Let's try another one. For each of the molecules, draw their Lewis structure and identify their number of electron domains and their electron domain geometries. So I give you the names. You're going to have to use the names to determine the formulas so you can draw the proper Lewis structure, okay? And then determine their domains and their geometry. Remember, we don't know lone pairs from our formula, so we have to write the formula first, count our electrons, and then determine if there's lone pairs on anything. So go ahead and pause your video, draw out these Lewis structures, and determine their domains and their geometries. Okay, again, I'm just going to draw the Lewis structures pretty quickly here. If your structure doesn't match mine, just double check you're following the rules correctly. So we have carbon tetrafluoride, that's going to be CCl4, so that's going to be carbon in the center, chlorines all around. I'm not going to show my lone pairs on my halogens right now just for time. We have sulfur trioxide, which is going to be SO3, so this is going to be S. I'm going to draw this in a way that looks like our geometry. Okay, and if you remember, in order to get my sulfur to have an octet, I'm going to take one of my lone pairs from my oxygen and move it down. Okay, so I'm going to just show that as a double bond to my oxygen, and then there's 2 lone pairs there. Okay, so it's sulfur trioxide. Then we have sulfur hexafluoride, that's SF6. So we have S, F, F. Again, I'm trying to draw this in a way that kind of looks like our geometry, not being very fancy in my artistry. So that's SF6. That's one of our expanded octets. So let's look at electron domains. Chlorine has 4 bonds, no lone pairs, that's 4 electron domains. Sulfur trioxide has 3 sets of bonds and no lone pairs, so that's 3 electron domains. And then sulfur hexafluoride has 6 domains because it has 6 bonds. So for electron domain, 4 electron domains is tetrahedral. We've done that a lot this lesson. 3 electron domains is trigonal planar. Okay, and then our final one for 6 electron domains, that's our big one, that's octahedral. Okay, so that's it for our lesson today on molecular structure. So before you move on to your next lesson, please make sure that you do your ALEKS homework and make sure you are mastering determining these structures and these geometries so that when we use it in our future lessons, you are prepared.